Okay, so this is now workshop 3, so I want to show you how to solve this. So we have in problem 1 is we have a roller coaster, and I hope I've been explicit about it enough about how this works. We have a roller coaster where the track is modeled by this equation, and not only by that equation, but also by this interval. So it goes from 1 to 7, and that's what the track looks like. So uh, we have the start of the track. We have some sort of spindle. It's just a reel that contains some rope, and as the roller coaster car moves along the track, it pulls along the rope. So my hope was that you would see just from the setup that what we're talking about here is arc length. If the arc length is really going to give the length of this track, then since the rope is just being dragged along by track, it's also going to give the length of the rope that's been dragged along. So we know what the formula for arc length is, and we know that in order to use it, we're going to have to find the derivative and square it, add one, and then put it under a radical sign. So let's start with f of x equals sine x squared over 10 plus 1. That's going to give us f prime of x is going to equal cosine of x squared over 10. And then by the chain rule, we need to do 2x times 1/10. So that equals x over 5 cosine of x squared over 10. That's the derivative. Let's come back here and we can see that f prime of x squared is going to be equal to x squared over 25 cosine. It's going to be cosine squared x squared over 10. In other words, I'm just squaring everything that you see in this equation. And that gives me the square of f prime. So if I wanted to find, this is not the question, but let's say I just wanted to find the length of the entire track, we would easily see that the length of the entire track is the integral from 1 to 7 of the square root of 1 plus x squared over 25 cosine squared x squared over 10 dx, right? Okay, so the that would give us the length of the entire track, right? But we're not interested really in the length of the entire track. What we're interested in is the length from the beginning of the track up to some point x. So let me show you how we would do that. The idea is that as we move x to the right, I want to get a larger number. If I move x to the left, I want to get a smaller number. In other words, that's what s of x really is. I'm saying let's define the length of rope that's been pulled out from the beginning up to some horizontal position x as a function of x. That sort of makes sense to do because if I change what x is, I'm changing the length of the rope. The length of the rope is dependent on how far horizontally I've gone along this track. So the way to do that is we're going to write s of x equals the integral, instead of from 1 to 7, which would give the whole length of the track, it's going to be from 1 to x. The question is what goes after here. The thing that I sort of suspected most people were going to do was this. They'd say, okay, well, it's 1 to x. Let's just put that same thing here. 1 plus x squared over 25 cosine x squared over 10, cosine squared x squared over 10 dx. The problem with this is that we're using the variable x in two different ways. When we use it, when we use the variable x here, oops, not what I meant to do. When we use the variable x here, what we're doing is we're representing as a variable how far along the track horizontally we are. When we use the x here, we're using it in the sense that it's used to define the entire length of the curve. So we have to use a different variable, and the way we do that is we just change what the variable is. So let's see. I'm just going to just change it. That's it. We're going to call it t. So every place that there had been an x in the original integrand, I'm just going to write a t. And that should make sense to you because think about this. I'm going to erase this because I don't want to clutter this up. But if you think about it, do you agree with me that the integral from 1 to 2 of x squared dx is equal to the integral from 1 to 2 of t squared dt, which equals the integral from 1 to 2 of theta squared d theta? In other words, it doesn't matter what variable I use. So this integral is going to be the same regardless of which variable I use. And I just want to make sure that because the problem asked for the length of rope as a function of x, where x was the horizontal, where's this? Where x was the horizontal position of the car, I have to use some other variable for the integrand. So there we go. So this is really the answer I was looking for. I'm going to erase this because I want this space here for solving the problem. Okay, so let's find s prime, the derivative of s of x. So we now know what s of x is. In order to do this, what you need to do is go back to section 5.4, and I put this up on Piazza, and some people asked me, and I basically directed them to this section. There was something in our textbook that most textbooks actually called FTC2. Our textbook calls it FTC1. I won't quibble over which one should be 1 and which one should be 2. Fundamental theorem of calculus. The part that you all remember is the part that says that the integral of f of x dx from a to b is equal to f of b minus f of a. That's the other part of the fundamental theorem of calculus. That's the part everybody remembers. The part that people often don't remember was this, which was sort of a necessary condition to be able to show that the theorem was useful. It's the existence theorem of antiderivatives. And what it says is that the derivative of the function a to x of f of t dt is equal to f of x. No antiderivative or derivative necessary. You simply take what's inside the integral and replace it. Well, that's exactly the situation we have here. We have s of x is defined in exactly this way, where this is just going to be the function f of t. So the answer is that s prime of x is equal to the square root of 1 plus x squared over 25 cosine squared x squared over 10. That's it. That's the answer. Okay, so for part C, the idea is to interpret what this derivative means. And we know about derivatives is that derivatives are about rates of change. Specifically, they're about, I want to say instantaneous rates of change, but I'm not sure that instantaneous is even necessarily isn't necessarily the best word here, because there's no time variable. And instantaneous is kind of a time concept. The point is we're not talking about the average rate of change over some distance. We're talking about the rate of change at exactly one point along this curve. The thing to recognize here is that derivatives are rates of change. It's a rate that something happens per something else. S prime of x can be written in other wording as ds over dt. You know this from Calc 1, or sorry, not dt, ds over dx. You know this from Calc 1. So the idea is that what this is equal to is the rate at which the length of the rope changes for every amount that the horizontal distance changes. And that makes sense because S is the length of the rope, X is the horizontal position of the car, and we know that the d operator before any variable should be read as change in. So this is the change in the length of the rope per change in the horizontal position of the car. That's the correct interpretation of this derivative. Okay. All right, so let's see now. Let's suppose that a bagel is formed by revolving the circle x squared plus y squared equals 1 about the line y equals negative 2. All right. What we want to do is we want to find the surface area of the bagel. This problem actually is easier than it looks because there's a lot of simplification that happens, but let's draw what we have here. So we have here the unit circle, that's x squared plus y squared equals 1. There we go. And we also have the line y equals negative 2. Okay, so we want to revolve this around the y-axis, and then find its surface area. That's what gives us, it's like really hard to draw this actually, but I'm not even going to try to draw it. It's impossible to draw. We all know what a bagel looks like. So basically I'm just, that's not helping. So basically we have, once again, this circle, this line, and we're taking that circle and revolving it around here, and it forms a bagel. It's going to be a bagel on its side. Okay, the thing to recognize in order to do this is that you don't have a function. You have really two functions. You've got the top and you have the bottom, and you have to do those separately. So the top part of this function is going to be, let's call that f of x. Let's call that f, yeah, call it f of x, that's good, is going to equal the square root of 1 minus x squared. That's just solving for y in terms of x. That's going to give, that gives the red part of the function. Let me circle it. I should have done it. I should have written it in red. The bottom part of the function, which is in green, we'll call that g of x, and that's going to be negative 1 minus x squared. Now, how do I do that? Well, I just solve y squared equals 1 minus x squared. That gives us y equals plus or minus the square root of 1 minus x squared. So one of these is going to be the plus, one of them is going to be the minus. All right, so what we need to do now is we need to do the, we're going to need the derivative so we can square them. So f prime of x is equal to 1 over 2 square root of 1 minus x squared times negative 2x by the chain rule. That equals negative x over square root of 1 minus x squared. G prime of x is going to equal, that's going to be negative 1 over 2 square root of 1 minus x squared times negative 2x. That equals x over the square root of 1 minus x squared. What we can see is that since this negative sign is going to go away when we square them, the square of f prime and the square of g prime are actually going to be the same thing. So we can say that f prime of x squared, which equals g prime of x squared, these are both going to be just x squared over 1 minus x squared, like that. Okay, so now we have to do the the surface area from rotating the top about this line, y equals negative 2, and we're also going to have to do the bottom. We're going to have to do the surface area of the bottom part, so we'll do those separately. This is going to be, let's see, the top is going to be the integral from negative 1 to 1 of 2 pi. Now recall the thing we multiply by is going to be the radius, so this is going to be the square root. Actually, that's correct. So this is going to be this is going to be 2 plus the square root of 1 minus x squared, that's the radius, and then times the square root of 1 plus x squared over 1 minus x squared dx. And the bottom is going to equal integral from negative 1 to 1 of 2 pi. If this was the top curve, the bottom curve is going to be the negative of that. How do we know? We go back up here and see that they're just mirror images of each other, so that's going to be 2 minus 1 minus x squared, and this is going to be 1 plus x squared over 1 minus x squared dx. Okay, so we have the top, this is the top surface area, and this is the top surface area, and this is the bottom surface area. Notice that these are almost identical expressions. The only difference is that one of them has a plus square root of 1 minus x squared, the other has a minus square root of 1 minus x squared. What that means actually is that this 1 minus x squared term and negative 1 minus x squared term, when we add these two integrals together, which we can do because they're on the same interval, they're just going to cancel each other out. So I'm just going to do that. I'm just going to add them together. And that becomes negative 1 to 1 of 2 pi. let's see, so I'm adding 2 plus square 2 plus this radical plus 2 minus this radical. The radical cancels out and I just get 4. And I'm going to simplify this expression just a little bit. So this is going to be 1 minus x squared over 1 minus x squared. In other words, that's just me rewriting this 1, and then plus x squared over 1 minus x squared. Okay, so the reason I did that, of course, is because I'm getting this cancellation. This negative x squared and positive x squared are going to cancel each other out. So this actually just becomes 1 over 1 minus x squared, like that. And I can rewrite that as the integral from negative 1 to 1 of 8 pi times 1 over the square root of 1 minus x squared dx. That's going to be 8 pi times, anyone recall what the antiderivative of that function is? That's arc sine of x going from negative 1 to 1. So that gives us 8 pi times pi over 2 minus negative pi over 2. This, of course, just equals pi, so the answer is 8 pi squared. That's the surface area of a bagel. Okay. And by the way, I guess I said that the distances are going to be measured in miles. This is one very large bagel, so the answer is it's 8 pi squared square miles, because that would be the unit of surface area for this bagel. Okay. Let us do this problem. Okay, so here what we have is we want to do a little bit of integration by parts and do it symbolically. So I've given you some values, but we don't know what this function looks like. We just know what the values of certain derivatives are. First one is fairly simple. We know that we just need, this is just going to be the antiderivative of f prime evaluated at 3 and 2 and subtracted. We know that the antiderivative of f prime is just equal to f, right? So this is going to be equal to f of 3 minus f of 2. That gives us, let's see, 1 minus 4, which is negative 3. All right. Now, for this one, this is probably best done by integration by parts. What I'm going to do is I'm going to let u equal x and dv equal f prime prime of x dx. Well, that means that v should just be the antiderivative of f double prime. Well, the antiderivative of the second derivative is the first derivative, or f prime. And then du is equal to dx. So that means that the integral of x f prime prime of x dx is equal to uv x f prime of x minus the integral of v du, which is just f prime of x dx. This, of course, is just f prime of it, is just f of x. So this is going to be x f prime of x minus f of x. So this is the antiderivative, and I simply evaluate that at 3 and 2 and subtract, because I'm asked to do it at 3 and 2. So this is going to be 3 times f prime of 3 is 2, and then minus f of 3, which is 1, and then subtract from that. Now I have to evaluate this whole expression at 2, so that's going to be 2 times f prime of 2 is 1, and then minus f of 2 is 4. So that's 6 minus 1 is 5, minus, that's 2 minus 4, 5 minus negative 2, and that gives us 7. And then do a very similar process for c. I'm going to let u equal x squared dv is equal to f triple prime of x dx. So v is equal to f double prime of x. Du is equal to 2x dx. So that means that the integral of x squared f triple prime of x, the antiderivative, is going to be equal to x squared f double prime of x minus the integral of minus, rather, 2 times the integral of x f double prime of x dx. Now, fortunately, we know from the previous problem what the integral of that expression is. So this is going to equal x squared f double prime of x minus 2 times this expression. So that's going to be minus 2x f prime of x plus, using the distributive property, so plus 2f of x. So now we're going to just evaluate that at 3 and 2 and subtract. So this is going to be 9. 3 squared is 9 times f double prime evaluated at 3 is negative 1 minus 2 times 3 times f prime is 2 plus 2 times f of x, 2 times 1, minus 2 squared is 4. F double prime evaluated at 2 is negative 1. And then minus 2 times f prime evaluated at 2 is 1. And then plus 2 times 4. So let's see, this is going to be negative 9 minus 12 is negative 21 plus 3. So that comes out to negative 18, if I'm doing my arithmetic right. And this is going to be negative 4. On the right, in the second parentheses, we have negative 4 minus 4 is negative 8 plus 8 is 0. So that's going to be, that comes out, that's convenient. So this should be negative 18. Okay. And then finally, we have this problem. We want to use integration by parts to rewrite sine 18th 3x in terms of sine to the 16th 3x. So we want to do this by integration by parts. So I first want you to explain why u equals sine to the 16th 3x would be a terrible choice of u. This is why. Let's suppose that I choose u equal sine to the 16th 3x. Then I have to choose dv is equal to sine squared 3x dx, because that's the only way I can make their product come out to sine to the 18th of 3x. So the problem with this is we don't really know yet, at least, how to integrate that. And remember what the main rule of choosing dv is you want it to be something that's really, really, really easy to integrate. That's the whole point of integration by parts, is that you're choosing something where you know how to integrate dv in order to convert an integral problem you can't solve basically into one that you can, into a part of a problem, just the dv part that you can solve, plus a differentiation problem on u. So the answer here is that this is a terrible choice because dv is not easy to integrate. Let me write that the way I would expect you to write it on. This is an awful choice because the resulting dv equals sine squared 3x dx, which is hard to integrate. There we go. All right, so now what we want to do is, now that we know why we wouldn't choose u equals sine to the 16th 3x, we want to choose it correctly and use u equals sine to the 17th. Sorry, I covered it up there. This is u equals sine to the 17th 3x to rewrite sine to the 18th 3x, integral of sine to the 18th 3x in terms of integral of sine to the 16th 3x. All right, so what we do is we choose u equals sine to the 17th 3x. dv equals, that gives us sine of 3x dx. That product now comes out to sine to the 18th. So du is equal to 17 sine to the 16th 3x cosine 3x times 3 dx. That's by the chain rule, by the way. Repeated application of the chain rule gives us that. And v is equal to negative 1/3 cosine of 3x. du we can simplify a little bit more. This is going to be 51 sine to the 16th 3x cosine 3x dx. Okay, so now we have is the integral of sine to the 18th 3x dx is equal to uv, so that's going to be negative 1/3 sine to the 17th 3x cosine 3x. In other words, this is all just uv. And then minus v du. Since the v is a negative number, I'm just going to convert this to plus because I'm going to be subtracting a negative number. So this is going to be plus 1/3 times the integral of, that's going to be 17, oh sorry, 51, I'm sorry, 51 sine to the 16th 3x cosine 3x, and then another cosine 3x. So that's going to be 51 sine to the 16th 3x cosine squared 3x dx. Now, I should point out that I can combine this 1/3 and this 51, so let me do that. That just gives us 17. So that's going to be 17 integral of that. Okay. Now, what we need to do is focus on this cosine squared. Whenever you see cosine squared in this class, there's a specific thing you should be thinking of. And that thing is cosine squared, I'll write it up here, cosine squared x plus sine squared x equals 1. You should be thinking about how to convert cosines and sines into each other. So let's see, so this is going to be the integral of sine to the 18th 3x dx equals negative 1/3 sine 17th 3x cosine 3x plus 17 integral of sine to the 16th 3x 1 minus sine squared 3x dx. Now, do a little more simplification. It's going to be negative 1/3 sine to the 17th 3x cosine 3x plus 17 integral of sine to the 16th 3x times 1 is just going to be sine to the 16th 3x dx. And now I can write another integral. This is going to be 17 times sine to the 16th 3x times negative sine squared 3x dx. So that's going to be minus, it's going to be minus 17 integral of sine to the 16th times squared give us sine to the 18th 3x dx. And note that I have now sine to the 18th 3x dx on both sides of the equation. So what I'm going to do is I'm going to add 17 of that integral to both sides of the equation. That causes it to disappear on the right side, but it gives me on the left side, it gives me 18 integral of sine to the 18th 3x dx equals negative 1/3 sine to the 17th 3x cosine 3x plus 17 integral of sine to the 16th 3x dx. Notice, by the way, that the question was to rewrite this in terms of integral of sine to the 16th dx, which now appears. The only thing is that what I have is I have 18 copies of sine to the 18th 3x dx on the left side, and I'm asked what one copy of that is. Well, that's fairly easy to solve. I just divide both sides of this equation by 18, and that gives me the integral of sine to the 18th 3x dx equals negative 1 over 18 times 3 is 54 sine to the 17th 3x cosine 3x plus 17 over 18 integral of sine to the 16th 3x dx. And there's our answer. And by the way, those of you who think maybe I'm missing a plus c, I'm actually not. The reason I'm not missing a plus c is that this integral itself is an indefinite integral, which sort of implies that there's an extra constant in here. So writing it again would just be redundant. It's already implied by the fact that I have an indefinite integral in my answer.